Hello, welcome to SEPAM. Today we're going to look at the part 2 of the model answer to IGCSE Physics Paper 4 Extended Variant 1, May-June 2024 edition. So we are starting the part 2 from question 5. If you have not gone through the part 1, I suggest you go through that so that you can now have a continuation from this part. All right, so let's jump in. Question 5. Describe how a longitudinal wave differs from a transverse wave. So what we're interested in is the differences between longitudinal wave and transverse wave. So what are the major differences? Longitudinal wave oscillates parallel to the direction of propagation of the wave, while transverse wave, the oscillation of the particle of the medium is perpendicular to the direction of wave propagation. So let's see, I'll explain that quickly. So what I mean by this is that if the wave is traveling to the right, then for longitudinal wave, the particle will vibrate to and fro, left to right, right to left, so in the same direction parallel to so this is wave direction, and then this is particle vibration. Okay, then for transverse wave, so I put that here. If the wave is traveling to the right, then the particle of the medium will vibrate up and down in this direction. So here this is particle, and then this is wave direction. Now, longitudinal wave consists of compression and rarefaction, while transverse wave consists of crest and trough. So based on longitudinal wave, like what you have here below in question 5b, which is a seismic wave. This is P seismic wave. This you have rarefaction, compression, rarefaction, compression where the particles are closely packed, rarefaction where the particles are slightly far apart, then compression. These are the alternates in the vibration. There's a video that I did on exploring longitudinal waves, so just watch out for it when I upload it to give you a better understanding of this. So I need to be fast so that the video will not be long, but at least you have the basic fact to answer this question. Okay, so let's go. The longitudinal wave need a medium to travel, while transverse wave does not need medium. So now let's look at the B part. So you have rarefaction. So what is the wavelength? Wavelength is the distance from compression to compression. And then in this question, they say the wavelength is 12 kilometers. And then all right, so let's continue. Now we have that state whether this seismic wave is a P wave or S wave. So this wave is a P wave and it is longitudinal. So, but S wave is transverse. So the representation here is the alteration of compression and rarefaction. So then let's look at the wave represented in figure 5.1 has a wavelength of 12 kilometers. Calculate the actual distance between point J and K. So between point J and K is 1.5 wavelength. So if one wavelength is 12 kilometer, then half wavelength will be 6 kilometer added to 12 kilometer, that will make 18 kilometer or 18,000 meter. The wave in question B2 travel through the ground at the speed of 4,600 meters per second. As the wave passes through a certain point, the ground completes 5 oscillations, that's 5 complete circle or vibration. Calculate the time it takes for the wave to pass through. So show your working. So all you need to do, what we have now is a wave that makes 5 complete oscillations. So if we have 5 complete oscillations, so you are having this, so you have one compression, then another compression, that is 1, 2, 3. So you have 1, 2, 3, 4, then 5. So now the time taken for it to travel here, this is the period T. And then, so once you know that the period T is equal to wavelength divided by velocity. So once you know the period, then you can now calculate the time taken for 5 complete oscillations, multiply the period, that there are 5 periods. So this question is all about looking for the period. So let's go. So the frequency, it makes 5 complete circles. So the frequency is 5 Hz. Then the velocity, 4,600. So we can get the time taken to make one complete circle, which is a period, is equal to 12 kilometers divided by 4,600 meters. So that will give you 2.5 seconds. So for 5 complete circle, that will be 5 multiplied 2.6 seconds. That will give about 13 seconds. Question 6. Figure 6.1 show an isolated metal sphere suspended by insulating thread from the ceiling. The sphere is negatively charged. The charge on the sphere produces an electric field in the surrounding. State what is meant by electric field. So you are looking at the definition of electric field. Electric field is a region where an electric charge experiences a force. So if you have this particular sphere and it's negatively charged, so if I bring out another charge close to this point, and this one is a positive charge, what the force that it will exert on this red charge is called, if you now divide the force by the quantity of charge, that will give you the electric field. So electric field E is equal to the force exerted per unit charge. Okay, so that's how the unit of electric field is Newton per coulomb. Okay, so that is the unit in the bracket. Now, having known that, so let's continue. It said, draw on figure 6.1 the pattern to show the direction of the electric field produced. Right. Now, what we are interested in is that if this unit positive charge that is placed here close to the sphere, which direction will the force pull it? And because the sphere is negatively charged, this positive charge will be attracted to it, so it's going to move towards the direction of that. So you have that. So negatively charged, so the field normally enter into a negatively charged particle. So that is the direction. So if you draw, they say draw any 4 line. Okay. Now let me just explain something that you need to know about field, the property of field quickly. Now, know is that field, when the line are close, this is a strong field. So this is strong field. Then when the line are far apart, this is a weak field. And then the arrow shows the direction of the field. That it shows the direction where a unit positive charge that is placed in this region, where will it move towards? The direction of motion. So that's the direction of the electric field. Okay. Now, this is a uniform field, but at times you can have a non-uniform field. So you can have something like this. So if you look at this, you have region A and then region B. So region B is the field is getting weaker, while at region A, the field is stronger. So you can have distribution of field in this way. So let's just go on. Okay, the magnitude of the charge on the sphere is 3.5 times 10 raised to power negative 10 coulomb. An altered metal wire is make a touch against the surface of the sphere, and then the sphere is discharged. State what happened in the wire as the sphere is discharged. So what we're interested in now, what show the direction of the flow of the electron, which is the charged particle. So if you have this, when a negatively charged metal discharges, electron move through the wire from the sphere towards the earth. So if you look at this is a charged particle. In this case, you have 1, 2, 3, 4. That is a net 4. Then you have 2 positively charged particle, maybe 3 proton, 4 electron. So the distribution of negative charge is more than that of positive. So it is negatively charged. So if you earth it, then connect a wire, then what happens? The extra electron flow, so remaining the balance of this. So this is electrically neutral, then the charge has gone there. So this process of turning a charged particle to a neutral particle is called discharging. So that is called discharging. Okay. Now let's go to B part, BII. It takes a time of 0.14 nanoseconds. So the trap here is nanosecond means 10 raised to power negative 9. Yeah. So for the sphere to discharge completely, calculate the average current in the earth wire as the sphere discharges. So for you to do that, you remember that current is equal to charge over time. So current is the flow of charge per unit time. And that will substitute the parameter that will give 2.5 seconds. So it will take 2.5 seconds for the sphere to be discharged completely. Question 7. The electromotive force EMF of a battery is 7.5 volts. Define the term electromotive force. Now the electromotive force is the electrical work done in moving a unit charge around a complete circle. The battery is connected in series with a variable resistor of resistance 30 ohm. The battery is made up of cells of 1.5 volt cells. Draw a circuit diagram to show all the 1.5 volt cells connected to produce an EMF of 7.5. Now, the basic thing you should know is that battery is a combination of cells. So how many cells are there? So you have 5 cells. You know, the long slash represent positive terminal, while the shorter slash represent negative terminal. So you have 5 of them connected together. How do you know that it's 5? If you divide 7.5 by 1.5, that will give you 5 cells. Then connect in series. So you have a resistor, 30 ohm resistor. Then you have the variable resistor connected to it. So now they are connected in series. So for this, you have your 3 mark. So now the resistance of the variable resistor vary from 0 to 150 using the axis in figure 7.1. Draw a graph to show the current in the circuit as the current varies with the resistance of the variable resistor. So now, since you know that the circuit that we have here, you have the battery. So for brevity of time, so let me do it like this. Then you have a variable resistor, and then you have the fixed resistor. Okay. And they say the resistance of this one vary from 1 to 150 ohm, and then this is 30 ohm. Now, if the resistance is 0, so what is going to be the current? So you can calculate the current. That will give a current of 0.25. So now how do we get the current? That is the EMF divided by the resistance. So when the EMF of the variable resistor is 0, so the total resistance in this circuit is going to be 30. So 30 divided 7.5, that will give 0.25 ampere. Then if the resistance of the variable resistor is now 75, so what will be the total resistance in the circuit will now be 75 plus 30, which is 105 ohm. If you use 105 ohm to divide that, that will give you 0.071 ampere. Then when the resistance of the variable resistor increases to 150, the total resistance in the circuit will now be 150 plus that will give 185. So if you have 185 ohm, 185 ohm divide 7.5 volts, that will give you the current of 0.041 ampere. So with that, you can plot this graph, the direction of the graph, that is from the current decreases as the resistance of the variable resistor increases. So question 8. The isotope thallium-208 is radioactive. It decays by beta decay. Thallium decay to an isotope of lead. Complete the equation for this decay. Okay, so if you have that, all we need to do is to balance the number of, so beta decay, what is the representation of beta? Beta is 0 minus 1. So if it releases beta, so you have that. So you balance the nucleon number. So 0 take away 208, take away 0. So that means the mass number of lead is going to be 208. Then you now go to the atomic number, that is the number at the denominator. So negative 1. What will I add to negative 1 to give me 81? 82. So with that, then question 8AII. The beta emission of thallium-208 is accompanied by gamma emission from the nucleus. Explain why this emission does not affect the number in the equation in AI. It's because gamma emission consists of wave, and gamma emission has no mass or charge. Now, suggest one reason why a nucleus of thallium this is unstable. Now, what's the proportion of proton to neutron is greater than 1, then the atom becomes unstable. So the reason is because the thallium has more number of neutrons in its nucleus. B, 8b. A sample of thallium fluoride is placed in a thick lead container. Now, to protect the operator from excess exposure to radiation, then show a narrow beam of this emerging from a small hole on one side of the container. Now, the narrow beam enter into a region where there is magnetic field. So now we want to see what is the impact of magnetic field on radioactive radiations. So we have the 3 radiations. What are they? We have alpha, beta, and gamma. But in this particular radiation, there is no alpha. So we only have beta particle and gamma radiation. So the beta will flip down, and then it deviates from the major part because beta is very light, and then gamma has no charge, and so the magnetic field does not affect it, so it travels and maintains the same direction. Question 9. The sun is one of many billions of stars in the Milky Way. The sun emits a very large quantity of energy as electromagnetic radiation. State the 3 regions of the electromagnetic spectrum in which the sun emits the most energy. We have ultraviolet radiation, visible spectrum, and infrared radiation. So how do you remember the electromagnetic spectrum component? You can use Remivus. G. So wavelength increases. So in this direction. So radio wave have the highest wavelength. So the major components where ultraviolet radiation, the radiation of the sun produces its radiation, those are the major components. Okay, now electromagnetic radiation from the sun travel at the speed of 300 million meters per second. The radiation takes 500 seconds to reach the earth. Calculate the distance from the sun. So once you want to calculate distance is equal to the speed of light times the time taken. So once you do that, that will give us 1.5 times 10 raised by 11 meter. Now, approximately 4.6 billion years ago, the sun formed from interstellar cloud of gas and became a stable star. Describe and explain what happened to an interstellar cloud of gas formed. So during the protostar formation, interstellar cloud and nebula collapsed due to internal gravitational attraction and internal temperature increase. Okay, now describe and explain what happened to a protostar for it to become stable. Then there must be a balance between the protostar become a stable star, nuclear fusion happen in the star, and then the forces between the internal force, the forces acting inward into the star core, and then the forces acting outward from the star core must balance together. So then the gravitational force acting inward balances the outward force of the high temperature that is coming from the nuclear fusion that is taking place in the core of the protostar. All right, thank you for going through this model answer with me. I want to encourage you to subscribe, like, and share this video, make your comments, and so that you keep updated when I upload any other video. And currently, I'm also offering a subscriber the opportunity to book an online personal coaching with me, Orishoje Matthew. So you can get this booking form in the description that's added to this video. Thank you for going through with me, and remain blessed and keep working. Success is possible.